We gaan het doen. We gaan de volgende kijken. Er staat Sapolsky, maar het is weer echt met mensen die het niet zijn. Het is echt verdrietig. Maar het leven is wat het is. Slimme dingen. Waar ging het over? Wacht, ik heb even gehad. Het gaat over neuroscience, deel 2. Pam, pam, pam. Ik weet niet waar het vorige keer over ging. Het ging het vorige keer over. Hersenen doen dingen. Ja, en dan gaan we meer leren over hersenen dingen doen.
I would like to get started, please.
Gesmikkelijk.
So,
Kijk, zie je het? Geen
my
Sapolsky.
name is Patrick House. I am
Kijk maar naar Afro. Pas van mijn baard.
a neuroscience PhD student. I work with Robert in Robert's lab. I'm a first year. And I study something that you guys will eventually hear about, but I don't want to ruin the punchline.
Oh, nee.
But today we're going to talk about memory and plasticity. And so two days ago on Wednesday, right, you guys all sat in here in this room, and you learned, some of you for the first time.
Op de temperature hoger zetten. Want dat doe ik ook wel wild.
Some of you for maybe the 10th time, the basics of neurobiology, of how a neuron works, how a neuron, you have a presynaptic cell, you have a postsynaptic cell, and this kind of simplified version of the communication and information transfer.
Ja, neuronen doen dingen met stromen en dat werkt zo. Dit is zoiets.
And something interesting happened between now and then, which is that now you sit in the same room, and something about you knows something about neuroscience now, right?
Yeah.
You heard one of the TAs talk, you slept on it, and then you come back now and you have assimilated, integrated into your identity, into what you know, new facts. And this lecture is about how you do that. And to kind of get at what memory is, we need to think about a lot of different ways in which it's interesting.
Hoe
A lot of
onthoud je
different
dingen?
kind of spectrums and severities about memory, right? So why is it that some memories last our entire lives, whereas other memories we hear and they're fleeting, they go away in a second? Why is it that someone's sitting next to you in bed telling you a story, and as you go to sleep, you can't remember it. As you wake up, you can't remember your dreams. But if that exact same person, that exact same story was told to you as they were sitting next to you in a car, and you get into a car accident, suddenly that memory becomes salient. You may remember it for years, if not your entire life, and you may actually associate either the story itself, the voice of the person, with that traumatic event, and you might get post-traumatic stress disorder. So the mechanism is the same between these two types of memory, between ones that are fleeting and forgetful, and ones that last your entire life. The question is, how does environment, how does context fit into shaping these types of memories?
Dat is ook heel interessant om te leren. Goh, hoe werkt zo'n geheugen en hoe kan je het weghalen? Want als je gedachten weg kan halen, door je heel PTSS op herinnering kan weghalen.
En
Volgens mij is dat ook de pil die ze echt zoeken om gewoon trauma's weg te halen bij soldaten, zodat je ze gewoon kan blijven gebruiken. Filosofische discussie in mijn hoofd over PTSS en het nut ervan, maar dat ga ik jullie besparen.
So in order to understand that, we have to kind of get at what are the mechanisms of memory and how are these contextually motivated. So I want to introduce to you first Stephen Wiltshire, who is an architect, if not in practice, at least in mind. He is an autistic savant, and he has been mute since age 3. And he has this remarkable capacity, which I'm actually going to test you guys on slightly here. If you have any kind of inclination to sketch, or you happen to have some sketch paper with you, I want you to, this will take approximately 60 seconds to span across all of Rome. Draw it from memory in your 60 seconds. Because Stephen Wiltshire has this amazing capacity to take helicopter rides. He's done this over Tokyo, he's done this over New York, he's done this over Rome and over London. And in 20 minutes, he can then sit down and recreate every single building, every single column, every single window in correct proportions from the correct angle in which the helicopter ride was. And so you may be thinking, okay, your 60 seconds are almost up. Can you guys do it? You may be thinking, okay, if any of you are artists out there, you may be thinking, this is unfair. Why can't I do this? And as neuroscientists, our first thought is, okay, this is unfair. Why can't I do this? But really, it can tell us something interesting about memory, right? So you come at it with two questions. First question, before and after this helicopter ride, what is different in Stephen's brain? And second, on this theme of individual variation that we keep kind of harping on in class, why is it that he can do this and we can't do this? And these are two important questions that if we could answer those questions, we would know a lot about what memory is. And so it really makes sense to kind of go back to what it is that we know so far about neurons, the basics of one neuron and how it is activated, right? And so we have a presynaptic cell and we have a postsynaptic cell. And in our simplified version, we can kind of know now, and what I'm going to tell you is that memory learning happens, to the best of our knowledge, in the synapse, in the place between the space between the pre and the postsynaptic cell. But to understand why it is that we think that, we kind of need to go back about 100 years.
Dat is wel cool dat ze weten waar dingen leren over het algemeen gebeurt. Dus pre- en postcellen, dingen, hersens.
When people, scientists, neuroscientists, were investigating the brain, investigating memory, and they thought that the smallest unit of the brain that they knew was the neuron. So because of our kind of tendency to explain what we don't know in terms of the smallest unit of thing that we do know, they thought, okay, this makes sense, right? A memory is a new neuron. And when you learn a new fact, when you learn the basics of neuroscience, you are growing new neurons, and each individual fact is associated with one new neuron. For instance, they may have thought that, okay, you guys learned on Wednesday that the axon hillock is the site of the generation of the axon action potential. So then that is a new fact, and then a new neuron would then be formed.
Yeah.
And okay, so that actually might not make. I just realized that actually might not make sense because at the time that they thought that, they didn't know what an axon hillock is. So maybe that formulation doesn't even make sense. But the idea is that.
Slechte docent, nee. Ja, ik vind het wel leuk. Hij doet het leuk, vind ik.
A couple decades later, people discovered the synapse. They discovered that neurons were not just one interconnected thing, that there was space, there's a gap between them. And as soon as they discovered the synapse, that then became the smallest bit of information we knew about the brain. And then theories came out saying, okay, well, no, memory must be the formation of synapses. So the dogma at the time was then that, okay, new fact.
Synapsen zijn volgens mij inderdaad de gebieden tussen neuronen in. En daar gebeurt shit met neurotransmitters. Volgens mij. Ik weet niet of neuronen zijn, maar in ieder geval een gebied tussen iets. En neurotransmitters doen de dingen. Dat is wat ik kan onthouden.
Axon hillock. What does this mean in the brain? You can see this in the brain. This takes the shape of a new synapse being formed. And what we think of now is that, well, this isn't exactly right because new synapses are not being formed all the time, and new neurons are not formed in the adult brain, which isn't entirely true, but we'll get back to that. But the idea is just that memory and storage of kind of learning, what I'm going to tell you is that it's in the synapse and that it involves modulation and change of the synapse. And why do we think that? Because we understand the molecules and we understand at a molecular level what's happening in a synapse when it changes. And so that is thus now our smallest level of understanding of the brain. And so of course we think, oh, well, that's probably where memory is. So that's the dogma that we're going to start with. And we're going to start with this idea that memory is synaptic plasticity. Memory is when the space between the presynaptic and postsynaptic neuron changes in some way. And not only that, it changes in one direction. It gets stronger, it's strengthened. And so what this means is that if you have your presynaptic neuron and you fire it, and you get some amount of response, that over time, if you give enough kind of presynaptic activation in a certain time window, that you will then get a heightened, strengthened response in your postsynaptic cell eventually. And that is the kind of mechanism, the overarching broad mechanism of LTP. And so what we need to do to understand memory is to focus on the synapse. So what we get is our kind of classical picture, which is that you have your synapse and a neurotransmitter is coming out, and that neurotransmitter is excitatory. And in your postsynaptic cell, what you're getting is you're getting a small amount of activation. You're getting current that comes into that cell. You're getting.
Dit volg ik wel een beetje. Wat ik zei, synapsdingetje. En dan gaat er neurotransmitters doen dingetjes. En dan zegt je hersenen van, oh, er gebeurt iets. En dat is waar die nu is.
Ions, some sort of response for any individual piece of neurotransmitter. And so what this is a version, a simplified version of what is called Hebbian plasticity. And so there's this guy, Hebb, which you have to know. There's a few kind of names you have to know in neuroscience, and he's one of them. And Hebb came up with this idea, the kind of only bumper sticker that neuroscientists ever have on their car, which is that neurons that fire together wire together. And what this is saying is that you have your standard picture of a very, very simplified version of a presynaptic cell that's releasing an excitatory neurotransmitter, and that when it does so, you get a response in your postsynaptic cell. And so if you will remember from kind of one lecture ago, that excitatory neurotransmitter is glutamate. And kind of, though, if you're going to spend any time and energy into remembering one neurotransmitter that might be relevant for the class, this is the one you want to remember. You don't have to remember it, right? So mostly the idea is just that it's excitatory. And why is this important is because information is transferred in the brain through activation. And in order to transfer information, you need excitatory neurotransmitters. You need your neurons to be activated. But as we know, kind of from what I've told you so far, that repetition is what drives memory, I would suggest that you remember that glutamate is the excitatory and one and only neurotransmitter that you have to know. That say there's a test question that says, what is the one excitatory neurotransmitter in the brain, that you have to know, you would respond glutamate, and you would be right.
Aardig als mensen dat doen, hè?
And so you can imagine that for this type of simplified diagram, if we were to strengthen the synapse, if we were to get some sort of plasticity, some sort of change, potentiation, what you could think of a few ways of doing this, right? You could take the presynaptic neuron and change how much excitatory neurotransmitter is released. You could change how much glutamate is released. And presumably, if you release more of the little circles with positive charge in them, then you're going to get more activation in the postsynaptic cell. Another thing you could do is write basic kind of neurochemistry in this diagram is that each of those neurotransmitters is binding to a receptor on the postsynaptic cell. And so what you can do is take that individual receptor and you can make it respond more to a single individual unit quanta of neurotransmitter. Alternately, you could just increase the number of postsynaptic receptors on your cell. And all of these would be mechanisms by which you could take this very, very simple synapse and potentiate it such that you get the same release, you get the same neurotransmitter, and what you get is subtle, because LTP is often very subtle. You just notice that the response is slightly larger, right?
Ook met die dingen zodat er meer gebeurt in je brein. Maar ik weet niet wat LTP is. Zullen we googlen? Iemand heeft zijn internet niet openstaan. What is LTP? Ik denk dat het gewoon dat neurolinguistisch programmeren is, maar... Nee, neuroscience. LTP, long-term potentiation. Ah ja. Gewoon dat het firewire together verhaal, dat het sterker wordt. Ja. Ja, iets met leren, zoiets.
Slightly larger response given the same amount of input, given the same amount of output of the presynaptic cell. And this is the entire idea of LTP, long-term potentiation.
Nou,
idea
godsamme wat. Gaat hij nou uitleggen?
That at your individual synapse, you can potentiate it, you can change it, it is plastic. But there should be one large red flag here, right? Which is, okay, one of these kind of caveats is, well, your presynaptic neuron, how does it know whether or not LTP should be undergone? How does it know whether or not LTP has been induced? This requires a kind of communication between both the pre and the postsynaptic cell, right? That how would the presynaptic cell, which has already released its neurotransmitter, know? And what you get is this kind of heretical type of neurotransmitter that can actually, we call it a retrograde neurotransmitter, that can actually be sent back from the postsynaptic cell. And it's a gas, nitric oxide is an example of one. It's what you get in your dentist. And it kind of goes back and diffuses back across the synapse and actually modulates how much neurotransmitter gets released from the presynaptic cell. So we have these mechanisms, right? We have these mechanisms of LTP. And the question then is, where does this happen in the brain? And why is it that we believe that these are the places of LTP? And one of the kind of things you need to know, this is our first kind of dive into neuroanatomy, is you need to know the hippocampus, right? It was introduced to you last lecture, but if there's one neurotransmitter you need to know, it's glutamate. And if there's one kind of neuroanatomical structure you need to know at this point, it's the hippocampus. And so how, I'm kind of always...
Hippocampus is dat ding waar je leert. Waar de dingen opgeslagen worden. Een van de weinige structuren waar je nog nieuwe cellen voor kan aanmaken. Ik weet niet of dat klopt. Nee, maar een van de structuren waar dat veel gebeurt. Neurogenesis. Zo, ik heb wat slims gezegd. Hoppakee.
Jealous of these autistic savants that can memorize 10,000 digits of pi and take a helicopter ride and then fully recreate the kind of cityscape of any city they see. And if you read interviews about how they do it, it's really interesting. So what they seem to do is not memorize just a sheet of a bunch of digits, a string of 10,000 digits of pi. They'll take a walk through their childhood town, and they'll say that they put one of the digits on each and every object. Right? So your mailbox will be the first digit, and then your neighbor's door will be another, and then their window will be a 3. And then they are not kind of reconceiving and reconstructing just a sheet of boring numbers. They're taking kind of spatial tours through their memory. And what this always kind of compels me to do is make these kind of visual mnemonics, right? So I'm going to give you a visual mnemonic for the one way.
Dit is ook legitiem. Ook gewoon, hier is ook echt onderzoek naar gedaan. De mnemonics zijn ezelsbruggetjes, maar als je een verhaal verzint bij dingen die je moet onthouden, kan je het beter onthouden. Dus als je 3 dingen moet onthouden. Oh, ik moet vandaag appels kopen en ik moet niet vergeten mijn moeder te bellen. En ik wil nog het vogelhuisje in elkaar mappen of zo. Dan kan je dus beter het onthouden als je, weet ik veel, je moeder in een vogelhuisje voorstelt. Terwijl ze met tegen een appel zit te praten. Boom. Dan kan je onthouden, vogelhuisje bouwen en appels kopen en mijn moeder bellen. Dus dan op die manier kan je dat doen. En dat is makkelijker dan die 3 dingen los in je hoofd onthouden. Okay, boom.
You have to remember that the hippocampus is the site of memory and the site of LTP, insofar as this class is concerned. Which is okay, hippo horse, right? We learned that last time. It looks kind of like a seahorse, but that doesn't really make sense. What if you think about this? What if you think about the hippodrome, right? Back in Rome, hippodrome was the circular arena where you had your little chariot races, right? Because of horse. And there's 2 different scenarios that I want you to imagine. The first is, you guys remember Michael Jordan and Larry Bird? They had this commercial where they played horse, right? And what they were doing is they were playing, you have to make a basketball shot, and then the next one you have to remember what that first person did exactly, and you have to recreate it, right? So what I like to imagine is Larry Bird and Michael Jordan playing a game of horse in the hippodrome back in Rome. And then you can kind of get this idea of how memory is related to the hippocampus and this horse structure. And if that doesn't work for you, I have one more, which is actually my favorite, which is you can imagine the entire amphitheater, the entire hippodrome filled with people. And there's that one emperor who named his horse a senator. Do you guys know who that is? What's his name? I don't know his name. Caligula, there you go. Okay, so imagine the entire hippodrome is filled with people, and Caligula is there, and he gets his senator horse in the middle of the field, and the horse is sitting kind of cross-legged, and he's typing out your memoirs, okay, on a typewriter. And that is how you're going to remember that the hippocampus, the hippodrome, the horse, is where memory is formed. Okay, so now you guys are all autistic savants now.
Ja, in ieder geval inderdaad, hij zoekt iets raars en grappigs, waardoor je brein iets makkelijker kan onthouden. Een donkey bridge, een ezelsbruggetje. Maar dan anders en grappiger met beeld in plaats van, weet ik veel. Wat zijn ezelsbruggetjes? I don't know, man. Geen idee. Maar er zijn ezelsbruggetjes waar je dingen makkelijker door kon onthouden. En dit met beeldjes erbij.
So, really though, we need to determine is, okay,
Je hebt het ook met gitaar. Dan heb je bijvoorbeeld op zeg maar de E en de A-snaar zijn de bovenste. En dan heb je nummer 7. Dat is dan de B en de E. De zevende fret, zeg maar. En dan zeg je, oh, beautiful elephants. En dan moet je altijd voorstellen dat je 7 mooie olifanten ziet. En dan heb je zoiets van, oh ja, zo kan je onthouden kan je snel onthouden waar die noten zitten. Want iedereen kan wel E, A, D, G, B, E. Dat is ook zo een aap die graag of geen. Maar ik vind het graag veel leuker. Bananen eten en dan kan je doortellen. Maar dan kan je dus eigenlijk zeggen, oh ja, 7 beautiful elephants. Kan je het heel snel doen. 3, maar ik weet niet wat ik mag zeggen, gay cats. Als je dat tegenwoordig word je dan gecanceld of zo als je dat zegt. Maar in ieder geval, dat heb je ook van, oh, hele leuke, gezellige katten maken, weet je, in je hoofd. En dat zijn er dan 3 van. En dan op die manier kan je dat dan onthouden. Zo doe je dat.
okay, why is it that we really think that the hippocampus is the site of LTP and memory formation? It turns out that there is actually adult neurogenesis and adult plasticity, right? So in the last 10 years, we've discovered that
Boom,
the adult brain really does actually form new neurons. And for the last 100 years, we kind of disregarded that and said those guys who initially believed that every new neuron is associated with every new fact, those guys were just totally wrong and ridiculous. What a ridiculous concept. And so perhaps eventually in the future, we will have to incorporate this idea that there does seem to be some neurogenesis in the brain. But much like how we learned that there is non-genetic kind of inherited traits, right? Which we had learned from kind of the disreputable Lamarck, way back in Lamarckian evolution, that there is no, for 100 years we thought, no, it's impossible. There is no non-genetic inheritance of traits. But it turns out that, well, okay, we do seem to have some kind of non-genetic inheritance, and so Lamarck isn't entirely wrong. And it turns out this is a kind of similar thing where the people of most disrepute are often just a little bit right. So probably people that used to think that adult neurogenesis has something to do with memory are probably a little bit right. But we're going to stick with the canon, which is that LTP happens, and that it happens not on the level of the neuron, not on the level of the synapse, but on the level of the plasticity of the synapse. And so why do we think it's the hippocampus?
Synaps die anders gevormd wordt, waardoor die andere dingen doet. En anders reageert op dingen, is wat hij volgens mij een beetje bedoelt.
We kind of get at it from a few ways. The first way is that HM, this kind of well-dressed epileptic who had his hippocampi removed, right? And what happened was he had selective removal of just his hippocampi, and he could no longer remember anything at all. He could not form new memories whatsoever. So with these types of conclusions, in addition to evidence that if you watch and record from neurons in the hippocampus as you're giving someone a
Klinkt zielig, maar die guy was volgens mij echt mega gelukkig, want hij leefde altijd in het nu en kon geen nieuwe dingen meer onthouden, dus hij was gewoon altijd blij. Dus op zich, veel van hem geleerd en hij was altijd gelukkig, dus wat dat betreft gewoon goed leven. Maar ja, goed, filosofie, ben je dan wel mens, bla 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 bla.
learning task, then you see LTP. If you pharmacologically block LTP, you see changes in the hippocampus. And so all these pieces of evidence are trying to get at the idea that the hippocampus is necessary for kind of memory and memory consolidation. But if you introspect a little bit, you can probably realize that, well, we undergo all kinds of forms of learning and memory, right? We have motor learning, we learn how to shoot baskets, we learn how to throw darts. We understand kind of emotionally that events that are more emotionally salient are more memorable. And so how is it that these types of things are also encoded in our brain, also encoded in the same region, the one region, the hippocampus? And what that turns out to be is that, well, it's not just that one region. LTP is happening all over the brain, that if you look in your emotional kind of regulation centers, if you look in your emotional cortices, you also see LTP. And this makes sense because these types of memories have to have different methods of storage and retrieval. And also that you can imagine this type of excitation, this type of synaptic plasticity can go wrong, right? In post-traumatic stress disorder, for instance, you get LTP, and you get LTP that is severe, and you get severe LTP, potentiation of your synapses, in those emotion regulation centers that create a situation where the context leads to memories that shouldn't necessarily be brought up, that shouldn't necessarily be retrieved.
Dat is interessant, ja. Want inderdaad, we hebben onderzocht dat dit zo werkt, en dan met PTSS werkt het dan zo. Dat je hersenen daar een beetje weird aan gaan doen, en dat heel vaak aanzetten, wat niet de bedoeling is, maar neuroplasticiteit en zo.
And so we see this mechanism for types of behavior that we know. Types of things like why memories last, certain emotionally salient memories last for a long time and others don't.
Ik denk aan OCD, maar ik weet niet of dat ik weet niet, ik ben geen neuropsycholoog.
And we can also imagine that this is a physiological process and that it can go wrong occasionally, right? We all know that memories are degraded, sometimes intentionally so, sometimes unintentionally so. That there are certain things we want to remember, despite any and all repetition about glutamate being the excitatory transmitter, we just don't remember them. And there are some...
Hij deed dat nu, dat is wel leuk. Het is inderdaad mogelijk om met herinneringen te fucken en dan kan je mensen echt overtuigen. Ik heb nooit onderzoeken zelf gelezen, maar dat is wel een ding wat vaak verteld wordt in psychologie. Dan kan je mensen overtuigen, dus dat ze vroeger bijvoorbeeld in een luchtballon hadden gezeten als kind of zo. En dan zeggen ze, oh ja, dat is gebeurd, ja. En dan krijgen ze er ook echt een beeld bij. Het is best wel weird. Met neppe kinderfoto's of zo deden ze dan. Best wel weird.
that just kind of fade away into time, into the oceans. And what is happening is that there are mechanisms for intentional disruption of LTP. And you can think of a few. So hypoglycemic states, if you are really, really hungry, you get insulin kind of cascades that end up reducing LTP. If you're starving, it's not a good time to try to remember things. It's a good time to try to go out and expend energy finding food. As we'll learn later in lectures, there are some stress hormones. And these stress hormones actually give us a selective memory advantage in the short term, right? If you're in a car crash, you remember the slow motion details of the entire event. And this has to do with these stress hormones, these fear hormones, coming out and saying, okay, well, we want to be able to remember this moment so we can learn from it next time if we survive.
Ja, zodat dit niet nog een keer gebeurt.
If you do this chronically, if you do this for a long time window throughout the lifetime of the organism, then you can actually get damage to LTP and damage to memory. So it's about time window. It's about these same mechanisms that can enhance memory can also be deleterious eventually. Another kind of probably more familiar one, perhaps not to the introverts, but perhaps to the extroverts in the crowd, is that if this lecture were on Saturday morning, I could probably ask you guys what you did last night, and some of you would not be able to tell me with delicate accuracy what happened on Friday.
Alcohol.
And you might not be able to tell me the story that was read to you at bedtime, or even who read you the story at bedtime. And this is because ethanol, alcohol, right, directly disrupts LTP. And we see this, and we see this in the hippocampus. And these are the types of things, behaviors that we know of, right? We know that emotionally salient memories last longer. We know that alcohol, somewhat, there are differential effects of types of substances on memory. We know that it's hard to remember things right before we go to sleep. And so what's interesting is, can we get at a physiology that explains all of these things? And so I'm going to give you 60 more seconds. There's going to be a pop quiz at the end, by the way. You have 60 more seconds to do this. And what is interesting here is that when we get down to these kind of physiological mechanisms, and we have two ends of a spectrum. We have HM, and we have Stephen Wiltshire, right? Someone who cannot form any memories whatsoever, and then someone who can do this in a 20-minute helicopter ride, recreate the entire landscape. And the question is, the theme of this class is often one of individual variation. How is it that one person can not be able to form any memories whatsoever? How is it that one person can have an autistic kind of photographic memory? And where do we fit? Where does memory fit in a properly functioning way? And like most of the kind of spectrums that are introduced into this class, right? One of
Normaalverdeling?
Imprinted genes, tournament versus pair bonding species, things like that. The answer turns out to be we are somewhere in the middle between HM, no hippocampi, no formation of new memories, and Stephen Wiltshire. So,
fuck it, terug.
That are introduced into this class, right? One of a properly functioning way. And like most of the kind of spectrums that are introduced into this class, right? One of imprinted genes, tournament versus pair bonding species, things like that.
Ja. Ik kreeg een blije flashback. Tournament species en samenwerkingsspecies. Van, we gaan alles samen doen. En of we gaan proberen zoveel mogelijk vrouwtjes te impregneren met ons zaad. En wij zijn koeler en bla bla bla. Of we gaan samen kinderen voeden. Mens valt daartussen. Jee, dingen die ik heb onthouden. Jee.
The answer turns out to be we
Of dingen onthouden. Dat is specifiek in het thema.
are somewhere in the middle between HM, no hippocampi, no formation of new memories, and Stephen Wiltshire. So, one more thing we need to discuss with the theme of this class is that often we'll give you a lecture, and then maybe in the next lecture, maybe kind of 5 minutes later, we'll tell you it's all wrong. Or we'll say, no, you've been way too myopic. That's not how you should see these things. And what we need to do in order to understand somewhat about the context of memories is to take and expand your myopic view of this simplified version of a neuron, right? So far, we've gone into what a single neuron functioning looks like. And we've gone into what a single neuron, as it transmits a signal to another neuron, looks like, how there's a gap in between the pre and the postsynaptic cell, and what that information transfer looks like, and how we can change that information transfer, how we can make it plastic. But there's a problem here, which is that if we're trying to learn anything about the brain, we have to understand that the brain is really complicated, and that there's 100 billion neurons, and that sometimes these individual neurons will connect to 10,000 other neurons. And sometimes each of those 10,000 neurons will have 10,000 neurons that connected to it. And so the question, the kind of first, I don't know, as a neuroscientist, when I look at that, the first thing I do is want to give up, right? And I do. And then the second question, the second kind of thought is, okay, maybe it's time to expand the simplified version of the neuron that we have. It's not just one neuron talking to another neuron. It's not just a single synapse, but that it's the dynamics of many, many interacting neurons. And that kind of as these dynamics expand, as these dynamics get introduced into 10,000 neurons at the same time, 10,000 dendrites, dendritic arbors connecting to 10,000 other like axonal processes, then we see that things that didn't matter so much in the single individual neuron actually matter quite a bit when you're talking about 100 billion neurons, right? So one of the things to introduce here is the concept of noise into the individual signal transfer, into the individual information transfer. A neuron, as we presented it, was something that fires an action potential, transmits information. Every single action potential leads to neurotransmitter release, which leads to a postsynaptic kind of response. But these are very delicate things, right? An individual neuron is constantly in flux with how much current is coming in and out, ions are flowing around. It's not as simple as a static neuron that then gets activated and then passes on a message to another static neuron, which then gets activated.
This complex.
What you get is often, a lot of times, you'll get random and spontaneous generation of signal, of action potentials, and sometimes of current in the postsynaptic cell. And one of the major tasks of the brain is figuring out what is signal, what is appropriate and meaningful signal versus what is this noise. If you can imagine on a single neural level, the noise might not have that much impact. But if you're talking about 100 billion neurons, you're going to get noise all over the place that will just kind of lead to this static of noise that you don't know what to make of the world anymore. You don't know what to make of the signal. You don't know what to make of individual neural signals. And so what we need to do is to start considering neurons in terms of how they interact in dynamics of groups. And one of the first ways and the most important ways to think about this is to understand that neurons are not just excitatory forces, that information, yes, is generated by kind of glutamate and the transfer of excitation, but that neurons have a capability to inhibit, right? And one of the important ways that they differentiate signal from noise, one of the important ways to learn what is noise and what is not, is to inhibit. And I'll explain how it is exactly that the inhibition works. But one of the first, oh, that's pretty high. One of the first ones to understand is that a neuron can inhibit itself, right?
Whoa.
Which is not really, it seems like it could initially be some sort of masochism, but it's really not. It's just that the neuron is trying to sharpen the signal that it's sending, right? So a neuron is firing and firing over and over and over. And what it wants to say, what it wants to be able to do is accurately give a precise description of the signal, of the information. And what it can do is inhibit itself to say, I'm done. No more spontaneous noise, no more spontaneous little bits of current. I am done with my signal. And what this is it allows for temporal sharpening. It allows for the ability of a neuron to say, this was my signal, it was meaningful, I really meant it, and inhibit the kinds of random noise and spontaneous things that could happen. Another aspect.
Je hebt mijn zegje gedaan.
Type of inhibition that's very important to separate noise from not noise is spatial inhibition. So what this is your individual neuron, not only can it send kind of processes and inhibit itself, it can actually send processes out and inhibit its neighbors. And how might this be kind of useful and important is that it can say, essentially, okay, this signal is real. This signal is the signal that I want to send, the information that I want to transfer. And not only that, ignore my neighbors, it's really me. And what this allows you to do is get spatial sharpening. So what this allows you to do is say, in the kind of field of things that you're trying to perceive, a certain neuron will respond to a certain section of that field, correct? And what this is saying is, I am activated, and you kind of inhibit your neighbors so that you're more sure that your signal is true. And how can we relate this? How can we make sense of this? There's a very simple type of feedback network that should kind of elaborate this idea, which is pain and pain sensation. And so we all probably at some point in our lives, presumably, have discovered and felt pain. And there's kind of two general qualities of pain. You can have really, really fast, sharp pain, and you can have this dull, aching, throbbing pain. And what people found when they investigate into your spinal cord and into kind of your sensory peripheral processes is how this pain is generated. And it's generated on two separate types of neurons. And one carries fast pain, one carries the sharp, fast stuff, one carries the slow, dull stuff. And what you find is that these are kind of intertwined in this delicate feedback loop such that the fast spiking first pain will generate kind of eventually the slow moving pain. It will fire the other neurons next to it, the neighbors.
Volgens mij heb ik hier legitiem een keer les over gehad tijdens een vak, maar ik weet niet zeker meer.
And say, okay, also start this kind of slow pain spike. But then the slow pain spike.
Want het was ook een manier om te zorgen dat pijn zou stoppen of zo. Als je chronische pijn hebt of zo ergens, als je dan een kleinere pijn doet, dat die chronische verdwijnt of zo. Ik weet het niet meer.
Can come back and inhibit the first kind of sharp spike such that it stops, right? We're trying to get information about the world, and your body is trying to do what it can with that information. And if you get stung by something, you want really sharp pain to be like, hey, pay attention to that, make sure it's not a scorpion that's still there. But you don't need the sharp pain forever. You want to be able to inhibit it and just say, okay, pay attention, but then, just to make sure you don't walk on it anymore and get it infected, we're going to make it hurt a little bit. And so this is your body trying to make the most of this type of information. And what it's doing is using lateral inhibition in this complicated way, actually simple way, to allow for these two types of kind of transmissions of information. That was a very simple example. And I think there's a much more complex example when we go into the types of complex kind of visual stimuli that vision gives us, right? And you can imagine that lateral inhibition, the same type of spatial sharpening of a signal, can come into play as we're trying to figure out and piece together the visual world. So what this is doing, what this kind of lateral inhibition allows for, is it allows for visual neurons to receive input and then to say, it is me, right? This is the signal that I want to send. Not only that, inhibit the neighbors. And what this leads to is this emergent property of these kind of retinal cells that allow for specific types of signal and allow for specific types of receptive fields. So in your eyes, your kind of neurons in the back of your eyes, if you just stand still, they only have a certain angle of light that they can get. And that idea is this idea of receptive fields, that they are responsible for that field, and they're responsible for saying, if there's a signal there, this is what it is, and this is how it's relevant. And what this type of lateral inhibition allows you to do is it allows you to say, okay, your neuron gets a signal, and it wants to say, okay, that's an edge detection, contrast detection. If you look around in the objects in the room, often you define them by their edges. So we have this elaborated kind of neural mechanism involving inhibition and excitation that allows for this type of contrast enhancement. And what can we do with this kind of even more, right? So these guys, Hubel and Wiesel, decided that they were going to look, okay, another brief anecdote. So there's this commercial when I was young, and it was Michelin tires, right? And if any of you guys ever become kind of marketing people, which there's enough of you that statistically someone will, I don't know why you don't make commercials that are scary, because this commercial frightened me, and I was like 6, and I remember it to this day. So why not, if you want someone to remember your product, just make it. Like, take what you know from this and use it to manipulate people. That's what education is. And so...
Dus ook echt, consumer psychology is ook echt een vak. En dan ga je dus ook leren over hoe je reclames maakt. Dan komt waarschijnlijk dit soort shit ook in naar voren. Het is echt psycho.
I remember this commercial, and I just remember it was for Michelin tires, and their whole point was that no matter how fancy your
Een hele master is daarop gebaseerd.
car is, no matter how much you spend on your car, there's only
Een jaar aan vakken van psychologie is daarop gebaseerd. Voor mensen die dat willen doen voor bedrijven, reclame maken.
4 points of contact between you and the road, right? And it's on your tires. And I don't know why, but this blew my mind, and it scared me. And it made me, okay, recognize that, yeah, you should get good tires. So Hubel and Wiesel, they took essentially the same logic, right? Which is that, okay, we have this complicated visual world, and we know that we put it together somehow. But our only access to this information is through the retina, right? We have, okay, the light is the road. These are our 2 tires, right? We only have 2 tires to connect with the road. And so their logic was that if we look at each individual neuron in the retina, and trace it back, we should be able to see somehow how this visual world is constructed. How it is that we go from the only signal from the outside world we get to this complicated visual field. And what they found was that if you look at the neurons in the back of a retina, and then look at kind of where they synapse back in kind of your visual cortex, they found a one-to-one correspondence. That if you activate a certain neuron in your retina, you'll get a kind of spatiotopic, which means they're oriented in the same way and all the neurons are aligned in a similar way, field in the back of your visual cortex in V1. And so what that essentially means is that kind of your eyes are smushed to the back of your head, right? There's no information that necessarily gets enhanced or reduced between your retina and the back of your visual field.
Whoa.
And they're like, okay, great. And so these guys, Hubel and Wiesel, they won the Nobel Prize. If you could win more than one, they probably would have won 4 by now. They're these Harvard neuroscientists back in the day, and they are pretty much the kind of who you need to know, right? You need to know Heb, you need to understand glutamate, you need to understand LTP. And Hubel and Wiesel, if you're going to be a neuroscientist, be interested in the brain, they will come up. And you have to, if you're a neuroscientist, you have to invite them to your wedding, and you have to do everything, right? I don't even know if they might even be dead. You have to seance them or something. But what they decided to do was then, okay, now we're at V1, we're at the 1 level of visual cortex. What else can we do? Where does the scene get constructed that we see? And what they did was looked 1 layer up. And they did the exact same thing. They fired individual retinal neurons, and they looked in the next layer up, and absolutely nothing happened. There's no activity anywhere. No matter what they did, they fired all of them, and there's no activity. And they were like, oh, damn it, we're not going to get invited to any weddings. And what are we going to do? But what they discovered was that if you kind of activated enough retinal neurons, and that they were in a certain spatial orientation, say a line, then you get activation in this other layer of your visual cortex. And what they discovered, and what was on, I'm sure, the construction of all of their wedding invitations, was that if you have certain neurons that are selective to certain orientations.
We hebben wel echt dezelfde humor als de Polski. Dat vind ik echt heel leuk.
Of lines, like so. If you imagine these are 4 neurons, a single neuron will be responsive to a vertical line, a single neuron, another one, a different one, will be responsive to a 45-degree angle, right? A horizontal line, 135 degrees. And so what you get, and you're starting to piece together, is this way of constructing the visual world that is layered, and that extracts out features, and that through those features, you get kind of individual neural activation. And you might imagine that if you go up even further, you would get some sort of more higher order types of activation, individual activation in your visual cortex. Something like, say, a neuron that only responds to an orange, or a neuron that only responds to a banana, or a neuron that, so this is one of the terms in the field, only responds to your grandmother, right? And they call it a grandmother neuron. And there's this kind of El Dorado type quest for grandmother neurons, right? Where can we find it? And the problem is nobody ever found it. And so then the question becomes, again, related to memory, related to even our understanding of these kind of networks of neurons, where are these memories stored? And so well, this is slightly out of order, but basically this is an example of, again, your lateral inhibition, right? So to understand how it is that these kind of signals are sharpened, right? This is a nice visual illusion. Do you guys see little dots of dark between each of those? That is an artifact, right? That is an artifact of your visual perception. That is an artifact of you constructing that. And why is that happening? Because at each of those individual corners, you're getting the most amount, because of the 4 kind of axial bars of white, of lateral inhibition. So in every single one of your brains right now, that whenever you look at the individual corner, you're getting lateral inhibition. And so you can imagine that this type of thing is a demonstration of lateral inhibition. Another type of thing, when I was talking about pain, right? So there's this
proberen te snappen, maar echt wat?
Fascinating thing where we all know this, where if something itches, say you have a mosquito bite, and you want to scratch the hell out of it because sometimes it feels really good, you notice also that you can scratch around it, right? You can make hard, kind of painful stimuli in the immediate vicinity and just do it really, really hard enough, and you get lessening of pain. And what that is the same type of thing.
Het is wel wat ik net zei. Wat ik les over had gehad, dus ik heb een soort van goed opgelet.
It's lateral inhibition of the focal point of the mosquito bite. And so these things sound
Laterale inhibitie, inderdaad. Dan had hij het over iets van, oh ja, het neuroon daarnaast, dan heb je dat beeld of zo. En dan heb je dat beeld. En die doet dat. En die doet een banderijn. En die doet je oma, whatever. En dan zit dus een neuroon te zeuren van, oh, ik heb een muggenbult. Het jeukt, het jeukt. En als je dan daarnaast pijn gaat doen, dan is het zo van, oh, ik heb pijn. Daar. Ik heb pijn, let op de pijn. En dan gaat de muggenbult weg.
abstract, but these things really are real. And we can see them and we can feel them if we know where to look.
Volgens mij.
So, one last idea, right? We're trying to get at, okay,
Oké, laatste idee. Daar is even pauze hoor, jongens.
where are these memories stored? Where are these facts? Where is what you know now about neurobiology stored? And we kind of, it's helpful to introduce the idea of neural networks, right? There's 100 billion neurons in the brain. These are not communicating one-to-one. These are communicating with dozens, tens of thousands of other types of neurons. And if you simplify this down to just the basic idea of a neural network, such that you have your kind of bottom first layer cells, and these first layer cells respond to, respectively, left to right, right? Monet, Cézanne, Degas. They just respond. For some reason, they have been tuned, they have undergone LTP. That is what they respond to, in this very one-to-one, Hubel-Wiesel kind of way. But what we notice is that there's this elaborate property you get when you start to combine neurons with many, many other types of neurons, which is that you get a network. And you get a network without one-to-one correspondence. So if you look at the top row and you get neurons A through E, A still responds in this one-to-one way with just Monet, right? E, again, you got just Degas. So those are not really informative in the way in which we want to understand the emergent property and what's important about neural networks. What we get out of neural networks is kind of emphasized when we focus on C, right? Neuron C doesn't know, if it gets activated, what can you tell? You don't know which kind of input it came from. You don't know whether it came from the first layer neuron 1, first layer neuron 2, or 3. You don't know whether or not it was a Monet, Cézanne, or Degas. All you know is that it's one of those three. And what you get now is this idea that you can have concepts, and you can have categories. And you can have a category of impressionism. That doesn't necessarily give you information about individual types or names, or which neuron it came from, but you have a network of neurons with different concepts in it. And amidst this network, you can now understand how it is that environment and context can impinge on the storage and retrieval of facts, right? So the idea that emotionally salient memories are kind of longer lived in your brain, in your synapses, in your kind of plasticity than other ones. Well, how is that true if they're not contextually related, if the mechanism is the same everywhere? But what you begin to see is that if you combine context in this version of neural networks, you start to get the neural representation of context, the neural representation of environment. And this makes sense if you think about how we try to remember things, right? If you try to remember something and you know it's an impressionist painter, or you know it's within a category, but you're not quite there, you kind of take a tour of categorical ways of thinking and categorical learning and categorical objects in the world to try to get at how that one fact, that one bit of information that you're trying to remember. So it's not that individual memories are stored in neurons. It's not that they're stored in the kind of the generation of synapses. It's not that they are stored in the entirely just the plasticity of single synapses. That it seems that we can get at and explain a lot of these types of memory by understanding that memory is kind of one aspect of the formation of these kind of neural networks, and that if we have 100 billion neurons, we can imagine elaborate and complex ways of designing these things. So here we go.
Oké, iets met dingen praten met elkaar, er komt meer context en je kan een soort categorisch denken. Maar ik ga het eerlijk zeggen, ik vind het toch grappig om te horen en over te leren en alles. Maar dit is nou weer niet echt de reden van gedrag of zo en alle verschillende stromingen. Het gaat er eigenlijk heel diep op iets in, wat ik eigenlijk denk van hoe erg interesseert mij dit. Maar fuck it, we gaan het afkijken. Oh my god, de volgende is ook die met Sapolsky. Daarna is hij weer terug tot het eind volgens mij. Dus dat gaan we afkijken. En die van volgende keer gaat over entrichronologie. Oké, whatever. We zijn nog niet. Fuck af.
One more time. Many very different things happen when we remember, right? Everything down from the synaptic plasticity all the way up to this impressionism categorical way of thinking and remembering about things. And what is, again, interesting here is that you can imagine what we've learned about polymorphisms, right? Genetic individuality and variation. That certain people can have different stress responses. You know, the person next to you can have a different response to stress than the other person. One person will be more afraid of public speaking than the other person. One person will respond a certain way based on prenatal, postnatal environment, all these different things.
Yeah.
All these different variations, these polymorphisms that lead to individual and varied behavior. And now we can understand that kind of a polymorphism in how much presynaptic glutamate gets released. Remember, glutamate excitatory. a polymorphism in how strongly your postsynaptic receptor responds, a polymorphism in the ways in which your kind of neural networks are constructed. These types of individual things, which each are their own variable in this kind of brain, in your brain's construct of memory, can lead to different and individual ways in which we remember. Some people are just better at remembering than others. And what we're trying to get at is from the spectrum of HM, who can't remember anything, to Stephen Wiltshire, who can remember this, and where the genetics and the environment kind of impact our individual memory.
Boom, best wel boeiend. Oké, mensen denken anders en ze proberen erachter onthouden. Eén kan beter dingen onthouden dan de ander. En de ene onthoudt beter deze dingen en de andere onthoudt beter deze andere dingen. En deze tak van wetenschap onderzoekt van, wow, hoe komt het dat dat verschil er is? Man, wat is de mens gespecialiseerd op sommige onderwerpen.
I think that's it.
Cool.
We'll take a 5-minute break.
Yay! Nou, ik vond het heel leuk. Ik ben helemaal blij dat hij dat gedaan heeft. Kijk, dit is een nieuwe persoon. Een dame.
Remember this.
Wacht.
And where
So,
Wacht,
Spawn
we
is like
beginnen
the
hebben. Oh, aapjes!
in individual ways in which we remember. Some people are just better at remembering than others. And what we're trying to get at is from the spectrum of HM, who can't remember anything, to Stephen Wiltshire, who can remember this, and where the genetics and the environment kind of
Even normale
impact our
snelheid.
individual memory.
Memory.
And I think that's it.
Yay!
So we'll take a 5-minute break.
Oké, wacht. Pauze. Ik ga even een ijsje pakken, want tegenwoordig eet ik ijs. Super lekker. En dan ben ik zo weer terug. Dus geniet van dit apenplaatje terwijl ik het geluid uitzet. Daar zijn we weer. En aapjes kijken. Even snel het hoger zetten. Wacht, eerst wil ik even de stem normaal horen. Dat vind ik gewoon cool.
And I'm going to talk to you guys about the autonomic nervous system.
Autonomic
So
nervous
basically,
system.
autonomic sounds like automatic. This is anything that's going to
Het is like parasympathische en sympathische zenuwstelsel.
happen automatically in your body. Not quite the hippocampus, horse, like hippodrome syndrome thing. Like we got automatic, autonomic. So basically, like your heart beating,
Ja.
digesting, goosebumps, orgasm, things that you don't have control over.
Orgasme!
That's good stuff, right? This is going to be your autonomic nervous system, okay? So, first, the nervous system, remember, is split up into the central and the peripheral. So our central nervous system is our brain and our spinal cord, and our peripheral nervous system is everything else on the periphery. And then within that, the peripheral nervous
Ja. Ja, dat is logisch. Even kijken hoor. Ja, in ieder geval autonomisch, sympathisch,
system can be split up into the somatic nervous system and the autonomic. So we're going over the autonomic, remember that. But just to tell you about the somatic, that's basically the voluntary nervous system. So like if you want to pick up a pen off the ground, you know your brain says, okay, I want to pick up a pen, send the message to my muscle. Muscle's going to pick up the pen. It's also your sensory info. So when you touch something or smell something, information from the periphery going to your central nervous system. And the autonomic nervous system, what we're going to talk about today, can be split up into the parasympathetic and sympathetic nervous systems. We'll go over all those in detail, but right now, one last comparison of the voluntary and autonomic. So the voluntary nervous system, remember, voluntary, moves muscles. Autonomic, it's involuntary, moving organs, your heart, your digestive system, your lungs. The voluntary nervous system is
En ademhaling is like de enige waar je wel controle over hebt dan.
actually myelinated. So what that means is there's a myelin sheath covering the axon, as you can see there, and the
Myelinscheiden.
action potential actually can speed up and go down the axon faster. And the autonomic nervous system is actually unmyelinated. These are just fun facts, so it goes a little bit slower. Okay, the good stuff. Autonomic nervous system. So we have sympathetic and parasympathetic. And like sympathetic is that nervous system where you hear fight or
And like, that is like that. That's like that.
flight. So anything exciting, arousal, alertness, emergency. Like if you have a hippo chasing after you or something, definitely sympathetic nervous system. If you like somebody and are like talking to them first time, sympathetic nervous system activation, you're excited. Parasympathetic is more of the calm, vegetative function. So after you have a huge
Wil je weten over seks? Ik heb een keer een soort van seksding over hier, hoe dat werkt ongeveer met die twee dingen. Want seks is natuurlijk ook ontspanning, maar ook like, je bent er wel even bezig, zeg maar. En het is een soort mix tussen die twee. En het is like, blijkbaar super complex. En volgens mij vlak voordat je like, een orgasme hebt, schiet je van parasympathisch naar sympathisch. Boom, dingen.
meal or when you want to take a nap, anything like that, growth, repair, just like total relaxation state. And as you can see, they kind of sound like they have opposing functions because they do, and they tend to work in opposition. So it's kind of like putting your foot on the gas and the brake at the same time. You can't really do that because they're opposing. When the parasympathetic system is on,
Behalve bij seks dus.
your sympathetic nervous system is usually off and vice versa. So they work together to like keep our body going automatically. Okay, sympathetic nervous system. So remember, this is like that huge animal, whatever your favorite one is, chasing after you. What do? Right? Well, your heart speeds up. It's going to beat faster. You're going to breathe more. You're going to vasoconstrict. So what that means is you're sending the blood. You're basically constricting your blood vessels and sending blood more to your lungs and to your muscles so you can run away. You're going to inhibit digestion. Like when you're running away from a hippo, like you don't care about digesting the sandwich you just had. You're going to sweat. Your
Soms kotst en scheid je ook, want dan ben je sneller. En dan dingen met vertering wat niet hoeft.
muscles will tense. Just anything you would think of when you're just like totally freaked out, right? And the parasympathetic nervous system. So yeah, I really like these pictures. I like found the dog and I got super excited. And then I found him and I wanted to name him.
Ik vind het wel leuk doen. Ik word hier wel vrolijk van. Ja. Rest and digest, growth, repair, ja.
I haven't thought of it yet, so. But basically, they're resting and digesting, right? They're just taking it easy, like growth, repair. Basically, anything you would do when you're not stressed, you have time to do now. Like your immune system can function well. You can spend time digesting and urinating. Okay. Sympathetic nervous system.
Yeah, urinating. Wel interessant. Ze zeggen altijd dat je immuunsysteem daalt bij stress, maar dat is niet helemaal waar. In het begin bij stress stijgt je immuunsysteem en bij chronische stress daalt die. En dat is logisch, want stel je voor je krijgt een wond en je wordt gebeten whatever, door een of ander beest, dan moet je een sterk immuunsysteem hebben, zodat niet je lichaam ziek wordt.
So we're going to look into the neurotransmitters involved
En als dat dus vaak gebeurt, krijg je een auto-immuunziekte. Oh my god.
in both the symptoms now. So like how on like neurons, like what's being communicated. And I know that Pat told you glutamate's the best, but I'm going to like fight that and tell you that norepinephrine is one of the good ones too. So basically, you release norepinephrine in the target organs when you're dealing with the sympathetic nervous system. So the hippo coming at you, right?
Noradrenaline.
What you do is you're going to release norepinephrine, NE, onto the target organs, and like you can see the organs on the left or the right, it affects all of those. So it's going to your heart, it's going to your lungs, it's going to your kidney, your bladder, and it's telling it when it receives norepinephrine, those organs know, okay, my sympathetic nervous system is activated. I'm gonna like fight or flight, I'm gonna run away right now, or I'm gonna start, like my heart's gonna beat faster. And one exception is the sympathetic nervous system actually releases epinephrine in the adrenal. And this is just a cool exception. Epinephrine, right? Remember, it's one step away from norepinephrine in the biosynthetic pathway, so you can make epinephrine from norepinephrine, so they're not really that different. And also, epinephrine is also called adrenaline, right? Adrenaline, see the resemblance?
Ooh.
And this is just another diagram again showing you norepinephrine released on the target organ. So you think of sympathetic, you think of norepinephrine. And you can see how it'll go and like accelerate the heartbeat, stuff like that. And just more in detail, if you've taken Biocore, and I don't know about home Biocore, but definitely Biocore, you know that it's not that simple. You don't need to worry about this, but there's actually
Gelukkig maar.
an intermediate step where the spinal cord projections actually first go to this ganglion, which then goes to the target organ and releases any there. But don't worry about that, just know norepinephrine sympathetic.
Kijk, dat is altijd leuk. Psychologie is er van, ja, een beetje de basis weten. Een docent legde dat ook uit. En die heeft dan zeg maar een dochter. En die studeert alleen maar biologie en allemaal zo. En dan zegt hij altijd van, klopt het nog? En dan zegt ze, ja. Maar het is wel een stuk ingewikkelder. Maar voor psychologie-studenten, gewoon prima, heel gewoon doen. En dan zegt hij, oké.
Okay, parasympathetic nervous system.
Okay.
So we have another cool neurotransmitter besides glutamate and NE, which is acetylcholine, or ACH. And the parasympathetic, you see it goes to all the same organs, but now when it releases ACH, those organs know parasympathetic, rest and digest. Like, I have time to, finish my meal and do everything that I can do when I want to relax. And again, there is an intermediate step where you release acetylcholine first in the target organ, and then a second neuron goes and releases acetylcholine again. There's no ACH parasympathetic. And if you want more details about it too, which this slide is totally extra details, but you can see like the projections from the spinal cord actually lead from different places in the parasympathetic and the sympathetic nervous system, and you can just see at the end acetylcholine and norepinephrine being released. Okay, so this is a really important slide. That slide put stars on it. Even Sapolsky, when he saw my PowerPoint, he's like, spend a lot of time on that slide, so I'm going to. Okay, so we're gonna look at exactly what happens when your parasympathetic or sympathetic nervous systems are activated and compare them to in like different organs.
Eigenlijk is dit een hele slechte PowerPoint slide, want het is echt like, super vol. Maar als ik even snel kijk, is het gewoon heel logisch. Maar dit is een beetje gewoon, hij zit ook altijd naar biologieboeken en zo. Het is gewoon eigenlijk heel simpel. Sympathisch activeert dingen, dus je pupillen doen dit en fucking huilen en speeksel en hart en bronchitis. Nee, je longen zeg maar die groter worden en je darmen en je blaas. Dat is wel interessant. Is je vaag? Ik vind het niet meer kloppen. Of is dit... Okay. Contracts bladder. Is je vaag dit? Ik ben benieuwd, want inderdaad, je ziet ook met ejaculatie en erectie en zo. Precies, kijk. Wel grappig, is een piemeltje daar. Piemeltje grappig. Erectie is dus inderdaad parasympathisch volgens mij, maar dan zie je dus ejaculatie is dus sympathisch. Dus dat is dan inderdaad dat samenspelding.
So the easiest one to start with is your cardiovascular system, so your heart, right? You're running away, you're scared, or you're meeting someone new for the first time that you really liked, and your sympathetic nervous system turns on. Your heart's going to beat faster. Remember that? So your heart actually has a myogenic rhythm, which means it actually has a muscle that is controlling its beating. But what the brain does and the sympathetic and parasympathetic nervous system does is it can change how fast the heart beats. So your heart's beating faster, your blood pressure will increase when your sympathetic nervous system is on. You're going to vasoconstrict, remember, send the blood to your muscles so you can run away, and all that good stuff. And parasympathetic, right? Opposite. Slower heartbeat, like vasodilation of the vessels. Blood's now going to the GI tract for digestion and everything like that. Another fun example is the GI tract itself. So your gut, your stomach, your small intestine. So
gastrointestinals.
Basically, parasympathetic activity, when you're resting, you have time to digest. So what you do is you stimulate the secretion of the acids and enzymes needed for digestion. You move your small intestine with a contraction called peristalsis. And basically, you can go to the bathroom and everything that you do while you're relaxing. And then, so, sorry. Okay, so in the heart and the GI tract, you can pretty much see that they're like working in opposition. So like when the heart beats up with sympathetic, it slows down with parasympathetic. GI, the opposite case, right? Parasympathetic turns it on.
Yeah. Yeah.
Speeds up digestion. Parasympathetic turns it off. I'm sorry. This is an important slide. Okay, so one place where they actually do work together instead of actually opposing each other is in the male reproductive system. And they work together for you to erect and ejaculate.
Boom, ik zei het al. Wow. Ik heb echt opgelet, man. Holy shit. Ja, dat zei je natuurlijk wel. Even kijken. Oké. Ja.
So what happens is, in order to have an erection, right, you have to be stress-free, you can't be worrying about your test. So which one do you think is in charge of erection, parasympathetic or sympathetic? Perfect. So parasympathetic activation, you get an erection. Okay? Now let's say...
Ik zei dit inderdaad al. Yay, ego groeit.
You have an erection, and now you're like with somebody maybe. I don't know what you're doing.
Maar wat ga ik ermee doen?
But like, whatever's happening, like, sorry. Okay, so your heart, like all of a sudden you feel your heart beating faster, you start sweating a little bit, right? Your sympathetic nervous system is turning on a little bit now. So now we have parasympathetic, we still have our erection, but like we also have some sympathetic activity, and then more and more sympathetic activity, and all of a sudden sympathetic activity completely takes over, and what happens?
Boom.
You ejaculate, right? So
Boom.
Parasympathetic erection, sympathetic ejaculation, and it's actually, the cool facts about erectile dysfunction is that about 60% of the cases are due to stress, and not actually organic basis in your body.
Ja, volgens mij checken ze dat ook, zeg maar, als je slaapt, dan krijg je een soort elastiekje of zo om je piemeltje heen. En dan zien ze of die los is gekomen of zo. Want in de avond krijg je altijd erecties, want je lichaam ontspant helemaal. Dus dan is dat parasympathische systeem super dominant aanwezig. Gaat ze dat nu zeggen?
Right? So if you're stressed out all the time, your parasympathetic activity won't turn on. So you can't have an erection. And also we can explain premature ejaculation if you want to your friends tonight. You can just be like, well, let's think about it. So I have an erection, but I'm going to ejaculate too soon. So parasympathetic transition to sympathetic transition, or the parasympathetic transition to sympathetic happens too quickly. Your premature ejaculation, okay?
Ook door stress of zo.
And then like health, right? So immune system. When your parasympathetic system is on, you can take care of your immune system, right? You have the time to make the white blood cells, but when you're chasing away from like a predator or like an elephant, you really don't care about making new white blood cells, and this could also...
Ja, en dat is dus bullshit eventjes, hè? Want je lichaam is zoiets van, als ik gebeten word, moet ik dat wel genezen.
Explain why it's easier to get sick when you're stressed out. Your sympathetic is like too much caring about your stressful...
Maar als het dus langdurig is, ja, dan zegt het lichaam op een gegeven moment, ja, oorlog overal, dan maar niet aan.
Situation than taking care of your immune system. Okay? I don't know. Oh, my computer goes on sleep.
Oké, dus hier, boom, heb je iets extra kennis. Dat door mijn hersens. Het immuunsysteem doet net ietsje meer in het begin van de stressrespons, maar daarna daalt het.
I think that's it.
Ik weet niet hoeveel tijd.
Okay, so again, we see there's a balance between the two branches. So sympathetic, you're running away from a snake. When that's on, parasympathetic's off, and vice versa. And there's actually a really cute video that I found. And you have to click it twice. Okay. So yeah. So the sympathetic nervous system, right? This video will tell you everything that I just told you. It increases heart rate.
Waarom krijgen wij het schattige filmpje niet?
Makes your pupils dilate so you can see further, run away from the predator. You don't have time to digest. You don't care about nasal secretions right now. You're not going to produce saliva. Who cares about eating? Inhibits the liver, kidneys, and gallbladder. And stimulates sweating, right? We're going to sweat when we're running away, getting scared. Causes piloerection, so when your hair stands when you're nervous. Makes the lungs dilate. You can breathe faster. Increases muscle strength, by the way, so you can run away. And it's important for orgasm. Sorry, I didn't want to...
Waarvan ze het sorry zegt, maar stress en whatever.
Okay, parasympathetic opposite, so it makes your heart...
Want het is eigenlijk heel enthousiast over iets. En dan denk ik altijd bij mezelf, schaam je daar niet gewoon voor? Own it. Dit is gewoon wie je bent. Geniet ervan, heb lol. Ja.
Rate go down, pupils are in contract, you're going to digest. You like the nasal secretions now. You're going to stimulate the liver, the bladder, and the kidneys. You can constrict your lungs, right? You're going to pay more attention to your digestion. And it's important for sexual arousal. Remember erections, okay?
Yay.
And you can play again later. I'm going to try it. Okay. So an important point to make is when we think about sympathetic nervous system, we're thinking about arousal, emergency, fight or flight, but that doesn't mean it always goes to the organ and excites it. So like, yeah, in the heart, when norepinephrine goes from the sympathetic nervous system to the heart, it does excite the heart and make it beat faster.
Yeah.
But when it goes to the GI tract, it inhibits GI tract activity. So it's not always excitatory, it's not always inhibitory. It depends on the organ. Same with parasympathetic. We think of it as being the slower moving one, but in the GI tract, it does excite it. In the heart, it inhibits. So what does that mean? That means we need two different receptors on our organs that respond to norepinephrine or acetylcholine. So on the heart, for instance, for norepinephrine, you'll have an excitatory norepinephrine receptor, because it will get excited and will make the heart beat faster. But in the GI tract, you'll have an inhibitory norepinephrine receptor that will respond to the sympathetic nervous system and slow it down. And then for the parasympathetic, you'd have an excitatory ACH receptor on your GI tract to speed it up, to digest more food. And you'll have an inhibitory ACH receptor on the heart to slow it down. So to see, you can't always have the same receptor on the same organ, or else it wouldn't respond right.
Kijk, nou zit ik altijd bij mezelf, van dit onderwerp weet ik gewoon meer af. Dus dan is mijn brein van, maar ik vraag me af of zij dan meer vertelt dan die andere guy, terwijl, of niet. Want als ik de kennis had over dit, had ik dan ook gewoon dat van die andere guy makkelijker gevolgd.
And this is just showing you again. So like the heart there, you have your inhibitory ACH receptor, which tells your heart to slow down, excitatory norepinephrine, heart speeds up. And then the GI tract, if like ACH is coming your way, it will attach to the excitatory receptor and it will like, digest. And you have the inhibitory norepinephrine receptor there too. So if sympathetic activity is being stimulated, norepinephrine will land there and it will slow down digestion. And so like if you've taken BioCore, if you want to know more, so there's actually names for all of these forms of receptors that I put there just in case you're extra interested. But on the heart, I think the coolest form is the beta blocker, or the coolest fact about it is the beta blocker. So the form of the receptor.
Dit doen ze nog wel, maar dat filmpje niet. Oh ja, specifieke namen. Dat is eigenlijk veel te complex, dat wil je helemaal niet weten. Ik ga er niet eens naar kijken. Ja, een beetje naar kijken, maar niks over zeggen.
On the heart that responds to the sympathetic nervous system is actually called a beta receptor. And what beta blockers do, right? They block the receptor, the beta receptor.
Oh, mijn brein zei dit. Oh my god.
Beta blockers are used for like slowing down heart rate, reducing hypertension, basically blocking the effects of the sympathetic nervous system. And Pat actually just told me, which is great, that the one drug that's like banned from the Olympics are actually beta blockers. Because if you think about it, like a huge advantage would be like to be less stressed. Yeah. So if they're blocking the receptor on your heart that like responds to stress and like the sympathetic nervous system, you can see how it could allow you to relax more. So it's a fun fact.
Maar dat is toch raar, want je hebt toch ook die energie juist nodig om je shit te doen dan. Nou ja.
Okay. So now we're going to talk about the regulation of the autonomic nervous system. So what's happening in the brain that's resulting in norepinephrine or acetylcholine being released. And the center of regulation is now the hypothalamus. So yeah, we just talked about the hippocampus. This is a different...
Ik denk dat ze het gaat hebben over de hypothalamus, pituitary, adrenal axis. En dat andere ding. Adrenal, whatever, I don't know.
Area of the brain, the hypothalamus. It's going to be very important on Monday as well when Tom and Will talk
maar dit is like je hypothalamus is dit. En je hypofyse doet er ook weer shit
about the endocrine system. Because the hypothalamus directly
endocrine is volgende keer.
Affects the pituitary gland, which is center of their endocrine system. So
hypofyse.
Basically, the hypothalamus here contains the cell bodies, or is just like one synapse away from all the cell bodies that project onto the target organs, right? From the spinal cord to the target organs. So basically, the hypothalamus will tell the spinal cord what to project onto the organ, okay? So an example of this would be like in your heart, and this is actually called the barrow reflex, and this is just an example of how your hypothalamus is going to help your body maintain status quo, so like make sure that your blood pressure is never too high, your heart's beating at a normal speed. So like let's say you're hemorrhaging, because, I don't know.
Big bloed.
Like a hyena just attacked you, and it's weird. So anyways, you're hemorrhaging, and you're losing a lot of blood, so your blood pressure is going to go way down, and you have these like receptors in your blood vessels. They're called baroreceptors, and they'll say, okay, blood pressure is way too low. What do? They're going to send that info to the hypothalamus. Remember the hypothalamus, center of regulation? And the hypothalamus will be in charge of sending that information along to the spinal cord, which will then project onto the heart and tell it to beat faster. Sympathetic nervous system will be activated. Beat faster, increase my blood pressure, so that you'll like make up for the loss of blood that you just had. Okay? And the opposite would happen if your blood pressure is getting too high or something. Maybe the info will be sent to your brain, and then you can decrease blood pressure through the parasympathetic nervous system.
Wat zeggen ze allemaal?
Okay, so
hyena, bijten, lager, maar dan toch hoger. Wat?
Reptiles, everybody kind of has that hypothalamus control of the, yeah. Oh, because remember like one's on or off? Yeah. So like, actually, like which one's normally on? Yeah. I think, do you guys know? Anybody know? Yeah. Okay, so.
Ik weet niet wat er gebeurde.
What about like mammals, right? Mammals have emotions, and we have an emotional regulation like area in our brain that's called the limbic system. And we're going to learn a whole lecture just about the limbic system in general, but basically...
Oh, dat wordt boeiend, want daar word ik gekut vanaf, maar iets met emoties en verzorging.
It has everything to do with emotions, behaviors, memories, all mammalian type things. And like, so now we see this realm where not just, you know, losing all your blood can activate or stimulate the nervous system and like cause a parasympathetic or sympathetic response.
Maar ook stress, emoties of zo.
But now just like seeing someone you hate, like causes a sympathetic response. It's very similar to like losing a lot of blood. And this is pretty amazing. Like wildebeest, for instance, if they see their enemies, they'll go, the info will be sent from just the smell of their enemies to the limbic system, project onto the hypothalamus, spinal cord, to the sympathetic nervous system, and be like, I don't like you, response. Like the sympathetic nervous system wanting to like either fight or flight, right? And then in the realm of primates, we also have our cortex. And what the cortex does is it makes thoughts and memories real.
Maar dit is een beetje het standaard ding van je hebt je reptiele brein. Dat is dat vechtvluchten, heel simpel. En dan je mammieten, wat? Je zoogdierenbrein. Je mammalbrein, je zoogdierenbrein. Die doet emotiedingen en verzorgingsdingen. En dan heb je neurocortex, whatever, dat freaking ding waar we nu zijn. En dat is mens/apen en daar doe je like complexe dingen mee. En dat gaat ze nu uitleggen.
Really important. So now, instead of just having losing a lot of blood, like changing how our body functions, and now just like not even having a sense. Like we don't need to have a sense, we can just think about a thought, and that can go ahead and change the way that every organ in our body functions, which is pretty amazing. So like when you're thinking about a test, for instance, you're gonna activate your cortex, and this will...
Wel eens mensen kunnen dat, en dat is ook best wel ziekmakend. Perseverance cognition of zo heet dat. In ieder geval, je denkt nou over iets stressvols en heb je gewoon last van. En een half uur later nog steeds.
Activate your limbic system, then your hypothalamus. So that's known actually as the triune system of the brain. Is you have the cortex in primates mostly, then you have the limbic system, mostly mammalian mammals, and then you have the hypothalamus, right? So it's going to go to each one of these layers of the brain, and just thinking about a test can cause a sympathetic response where you start sweating, getting nervous, stressed out, and it's pretty amazing that just like if you lost a lot of blood in a reptile, that's we can stimulate the same response just thinking about something or thinking about something on the other side of the world dying. It's just amazing what like primates can do. And an interesting example of this, and I think we're having a lecture on depression, so I don't want to give it all away yet, but if you think about it, like the symptoms of depression.
Is die er? Ik zal even kijken. Nou, niet specifiek in ieder geval. Nou ja, whatever.
Loss of pleasure, pain pathways on, don't want to have sex, aren't in the mood to eat, you're exhausted all the time. A lot of these symptoms are the same symptoms you would see if your sympathetic nervous system was overly activated. And we can see how a cortex, having bad thoughts, can go and activate that system in the same way, links to depression.
Ja, dat is ook best wel een ding altijd. Mensen, zeg maar, stress is best wel gelinkt aan depressie. En dat maakt volgens mij burn-out vaak ook een beetje complex om het te onderscheiden van depressie. Hier, kennis, doe er wat mee.
Okay. And the last thing I wanted to talk about in terms of the autonomic nervous
Ze doet telkens een of ander hupsje of zo. Zien jullie dat?
activate that system in the same way, links to depression.
Hier, daar gaat het hupsje. Wacht even hoor, die wil ik even zien. Even hupsje. Komt-ie, hè?
Okay. And the last thing I wanted to
Even hupsje naar
talk
beneden.
about in terms of the autonomic nervous system was the plasticity of it.
Even hupsie. Even een hupsie. Hoor.
So we just learned like the plasticity, right, in neurons and the synapses. So this one can change over time, and the autonomic nervous system can actually change over time in terms of how receptive or when it turns on and off. And a molecular example of this is if like you're a very stressful person and you're stressing all the time, well then you need a lot of norepinephrine, right? What do you do if you're stressing all the time? You increase the synthesis of the enzyme called tyrosine hydroxylase, I believe. Yeah, it's up there. And basically this is the rate limiting step in
Het is wel echt slim hoor, want als je dat onthoudt is het gewoon knap.
making norepinephrine. So if you increase more of the enzyme, you increase more of the norepinephrine, you can sustain the stress response. Another example, cellular example, is that we have projections from the sympathetic nervous system to the skin, eyes, nose, like everything that's going on out there. And let's say we see something scary. We can make those receptors more sensitive to that scary thing. So we can say, hey, it actually smells that enemy. Like we can make it seem scarier, and the sympathetic nervous system can turn on faster. So sensitization. There's also the opposite end of the spectrum.
Desensitisatie. In ieder geval, ze zegt nu dingen als... oh, je brein ruikt iets en reageert daar sneller op. En als je autonome zenuwsysteem, zeg maar, dat was dat ANS, is Autonomic Nervous System, dat anders gaat reageren op bepaalde prikkels, omdat je er vaker mee in aanraking komt of iets dergelijks. Dus als je heel vaak, weet ik veel, in een omgeving is waar like, tijgers zijn of zo, dan ga je sneller op iets wat op een tijger lijkt, sneller gestrest reageren, want ze zijn eng.
Where like you habituate to things that are going on outside. So like scary stimuli. Like if you see a spider in your room the first time, you're probably going to freak out when you're younger. And lots of sympathetic activity, running away, fight or flight. You decide to fly.
Maar spinnetjes, op een gegeven moment heb je ze wel gezien en denk je, ja, die doen toch niks hier en het zit wel goed.
Because I don't like spiders.
In Nederland. Ja, dat dacht ik
But
al.
basically after a while, the second time you see a spider, you're just like, okay, this is still scary, maybe I'll run away. The third time, maybe you'll like decide, whatever, I'm just going to leave it there at this point, and you're habituated to it. So you've made the thresholds of your sensory receptors, like they don't care as much, they don't respond as much. And a last example, when we're talking about cognitive thought and the cortex and what that can do to change your autonomic nervous system, is an example of biofeedback and blood pressure. So basically, if you have high blood pressure, you can go into the doctor's office and you have two options, right? You can take medicine.
Deze dat hupsje weer. Zag je dat hupsje? Weer hupsje. Dit is hupsje hoor. Komt-ie.
Basically, if you have high blood pressure, you can go into the doctor's office and you have two options, right? You can take medicine or you can try biofeedback. And what they do is they like...
Biofeedback is volgens mij dat je een filmpje kijkt of zo en als je lichaam dan doet wat het moet doen, dan heb je een helder beeld en als het dat niet doet, heb je een niet helder beeld en dan reageert je lichaam daarop of zo.
Tell you to think of a pleasant thought. So like think of your favorite vacation or think of your favorite person or just think of the beach in general. And what you'll see is that your blood pressure will actually decrease with a certain thought. And then the doctor will tell you to think about that thought again, your blood pressure will decrease. And thinking more and more about that thought helping your blood pressure decrease, what you do is you potentiate, remember, you make stronger the connection where a cortical thought can go ahead and like activate more parasympathetic tone, have less sympathetic tone. So we're like potentiating that pathway by which a thought can cause our blood pressure to decrease, which is really cool.
Oh ja, oké. Dus dan krijg je gewoon een automatische reactie op die gedachte dat je bloeddruk verlaagt. Iets anders dan wat ik zei. Maar biofeedback, dat is dan wat anders, whatever. Maar of het kan ook op die manier, dat op meerdere manieren kan. I don't know. Ik ben geen biofeed expert.
Okay. So take-home points, if you want to just like know what to remember from this. Know the broad difference between automatic, right, and the voluntary nervous system, what we talked about at the beginning. Understand the neurotransmitters involved in each and why you need two types of receptors, right, the inhibitory and excitatory. Know one or two examples of what the parasympathetic, that's what PNS, by the way, means.
Deze?
And why you need two types of receptors, right, the inhibitory and excitatory. Know one or two examples of what the parasympathetic, that's what PNS, by the way, means, and sympathetic nervous system do to an organ. So remember the heart, the digestive tract, the male reproductive system, and then know a broad overview of how the brain regulates the autonomic nervous system. So hypothalamus, cortex, right, and we have the limbic system. Okay, and on Monday we're going over endocrinology, and so have a good.
Oké, dat was
For more,
het weer.
please visit.
Ik wil even kijken of ik die vragen kan beantwoorden. Of ik hersenen voor heb. Oké. Oh nee, kan ik dit? Weet ik eigenlijk niet. Grootste verschillen tussen autonomisch en voluntary. Oh ja, oké. Maar dat is toch heel simpel. Autonomisch gebeurt automatisch en voluntary doe je zelf. Voluntary is, oh ik pak dit ding op. En autonomisch is like, oh ik heb er geen controle over, los van mijn ademhaling, want whatever. Neurotransmitters. Oh ja, dat wordt wel een beetje. Oh ja, dit is wel een beetje. Wordt het al wat complexer. Nou, in ieder geval. Epinephrine en norepinephrine doet shit. Maar is dat al een neurotransmitter dan? Dat weet ik eigenlijk niet. Even kijken hoor. Ja, precies. En wel, waarom twee types? Dat is wel logisch, want op de ene moet hij zo reageren en moet hij activeren. Op die andere moet hij juist kalmeren. Moet hij minder actief worden. Dus dat is logisch. En dan inderdaad. Hartslag die sneller gaat of langzamer en longen die groeien en hoe heet dat, uitzetten of minder uitzetten. Vertering en natuurlijk een erectie en orgasme. Broad overview of brain regulates autonomic nervous system. Ja. Dat zijn die lagen dan, maar ja. Je ziet dingen en dan kom je eerder, ik weet niet, een beetje vaag. Whatever. Ik weet er nog best wel over. Dat vind ik leuk. Jippie. Zou zo op Stanford kunnen studeren. In ieder geval, dit was het. Ik heb gelachen weer. Ik vond het wel leuk om dit even te kijken. Ik heb genoten. We moeten er nog. Even kijken hoor. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 14. 14 stuks. Dit was wel weer een... Oh, er komt er echt even een 1,5 uur daar. 1 uur en 40 minuten. Oh shit. Die gaan wel over seks, dus dat is wel boeiend. Ja, er komt heel veel over seks en agressie nog. Die doen echt super lang. En je moet allemaal in één keer gaan kijken. Jezus. Er komt echt een lange weer. Ja, wat grappig. Oh wauw, oké. Ik dacht dat de lange een beetje voorbij waren, maar die zijn niet voorbij. Die gaan hierna nog komen. En dan laatste dan weer kort. Nou ja, whatever. Alles op tijd. Was gezellig. Tot de volgende keer. Samenvatting. Heb ik een samenvatting? Ik weet het niet. Ik vind het allemaal goed. Allemaal helder. Whatever. Doei.